In this example, we have a painting hanging from a ceiling by two strings. The configuration of the strings is given in the diagram there. And the question is, what's the tension on each string? Now the painting isn't moving, so the sum of the forces on the painting must be equal to 0. Let's think about the forces that are there. Each string exerts tension, pulling the painting up. So the string on the right exerts a tension, we'll call that T1. The string on the left exerts a tension, we'll call that T2. And gravity is pulling down on the painting. We'll call that W. We're given the magnitude of W. The painting weighs 50 newtons. So to figure out the tensions, all we have to do is figure out what value T1 and T2 have to have so that all of the forces on the painting sum to 0. The problem is this is a little annoying because T1 and T2 are two-dimensional vectors. Weight's pulling straight down, but T1 and T2 are pulling at angles. So we have to analyze the components of the vectors and make sure all the horizontal components add to 0 as well as all the vertical components. So let's start by taking T1 and T2 and splitting them up into their components. The horizontal component of T1 is simply the magnitude, T1, times the cosine of the angle, 45 degrees. That works out to 0.707 times T1. The y component is the magnitude, T1, times the sine of the angle, 45 degrees. That also works out to 0.707 T1. Now doing T2 is a little trickier because the angle is not defined properly. Remember, in vector addition and subtraction, we always want to define the angle from the positive x-axis. Right now, the angle of 45 degrees is defined from the negative x-axis. So we would really like to define an angle from the positive x-axis, the angle shown in red. What's the value of this angle? Well, think about it. From the positive x-axis to the negative x-axis, the total angle is 180 degrees. 45 degrees of it is already taken up. So that red angle must be 135 degrees. That way 135 plus 45 is 180. So everything works out. So our properly defined angle for T2 is 135 degrees. Now we can break T2 up into its components. The x component is the magnitude, T2, times the cosine of the angle, 135.0 degrees. That gives us a negative 0.7071 T2. The y component is the magnitude, T2, times the sine of the angle, and that gives us 0.7071 T2. So those are the x and y components for the tensions, but we also need to get the x and y component for the weight. The weight's pointing straight down. That corresponds to an angle of 270 degrees. So the x component of the weight is the magnitude, 50.0 newtons, times the cosine of 270 degrees. That turns out to be 0. And the y component is 50.0 newtons times the sine of 270.0 degrees, which turns out to be negative 50.0 newtons. Okay, so those are the x and y components for all of the vectors involved. Let's summarize them at the top of the board. Now we have to make sure that these x and y components all sum to 0. Let's start by looking in the x dimension. The sum of all forces in the x dimension has to equal 0. Well, T1x is 0.707 times T1. T2x is negative 0.7071 times T2. And Wx is 0. All three of those forces have to add to 0. So here we have an equation, but unfortunately there are two unknowns. We don't know T1 or T2. However, we can solve for T1 in terms of T2. If I add 0.7071 times T2 to both sides of the equation, I find out that 0.707 T1 equals 0.7071 T2. If I divide both sides by 0.707, I find out that T1 equals T2. So even though I don't know what T1 and T2 are, I know they equal each other. That tells me something. Now let's move to the y dimension. The sum of the forces in the y dimension also must equal 0. Well, T1y is 0.707 T1, T2y is 0.7071 T2, and Wy is negative 50.0 newtons. Those all have to sum to 0. So now we have another equation with two unknowns. However, that shouldn't be a problem, because as you should remember from Algebra 2, if I have two equations with the same two unknowns, I can solve them simultaneously. Let's actually summarize the two equations we have. From the x dimension, we learned that t1 equals t2. From the y dimension, we learned that 0.707 t1 plus 0.7071 t2 minus 50.0 equals 0. Those are our two equations. We can solve these simultaneously. How do we do that? Well, let's start with the second equation. Let's add 50.0 newtons to both sides. That gives me 0.707 t1 plus 0.7071 t2 equals 50.0 newtons. Now let's look at the first equation. The first equation tells us that t1 equals t2. So anywhere I see a t2, I could stick in t1. They equal each other. So in the second equation, let's replace t2 with t1. That gives us that 0.707 t1 plus 0.7071 t1 equals 50.0 newtons. Well, all we have to do now is add the two t1 terms together. That gives us that 1.414 times t1 equals 50 newtons. Now it's easy to solve for t1. Divide both sides by 1.414 and you get t1 equals 35.4 newtons. Well, remember t1 equals t2, so that means t2 is also 35.4 newtons. So those are our answers. The tension on each string is 35.4 newtons. Now this is a long drawn out problem, but really it's only a long drawn out problem because we first have to split the vectors up into their components and then we have to solve two equations simultaneously. If you're having trouble with that part, solving two equations simultaneously, you might want to look back at your Algebra 2 book because we'll be doing that a lot in this module.